Welcome to today's webinar on 3 real-world data projects for your portfolio. My name is Darren, I'll be your moderator, and with us today are 3 experts from Omdena who are going to go over some projects that you can analyze in the spirit of how to expand your own data project portfolio. Okay, so in today's session, we're going to go in depth into 3 data science case studies to look at how to leverage data science for decision-making, innovation, and meeting customers' needs. We hope that these case studies will help you prepare for that very critical moment in your own data science job interview, the portfolio review, which if you've done any of your own research or have followed along with what the conversations that DataQuest leads on social media, the portfolio is an essential part of landing your data science job. It's really what shows that you have the chops. It doesn't matter how many certificates you've acquired or how many boot camps you've been through. If you can't actually use your data skills, then you are of no use to the employer. So our agenda for today is we're going to go over these 3 case studies. You can see them listed there on your screen. And my first question is going to be, what is a real-world data project? So I would like to take this opportunity to invite our speakers to introduce themselves, and then we'll get going. Rosana, go ahead.
So hello, everyone. This is Rosana. I am a former collaborator from Omdena, and I'm also senior data scientist at Hacon Time series here in Vienna, Austria. One fun fact about me, I am an astronomer for training, and then I transitioned into a data science career. So I think I'll pass over then to Sai to introduce himself.
Thank you, Rosana. Hello all. My name is Sai. I'm a product lead with Omdena, and I'm also a cloud solutions architect working with S&P Global Market Intelligence Company. Thanks for having me, Darren and DataQuest. It's a pleasure to be here and share screen space with wonderful co-speakers, Rosana and Srirupa, who are doing some amazing contributions to the AI community and also creating a social impact. Looking forward to see how the session turns out and help the audience get better. Yep, looking forward. Thanks.
Hi, everyone. This is Srirupa. So I am a senior machine learning engineer at Mercedes-Benz Research and Development India. I've been in this field for approximately 4 years now, and I have transitioned fully to AI and hope to build a very successful career out of AI moving forward. One fun fact about me, I'm not sure if this is fun, but my dream is to sort of build AI models out of astronomical data and sort of predict the next Earth in the universe, if that at all sounds fun. Yeah, so that's pretty much about it, and very excited to see how this webinar goes. Nice to meet you all.
Thank you, everyone. As I said at the beginning, my name is Darren. I am the least important member of this panel. I'm just here to keep time and facilitate our friends. I'm the managing editor at DataQuest. So with the introductions out of the way, let's go ahead and get started. We'll go back to my question, which is, what is a real-world data science project? Please take it away.
Yeah, I think that for me, especially I have a former career in research in astronomy, as I mentioned before. So to me, I think that real world is something that has a clear application. Of course, like when you work with research, you are exploring kind of abstract problems, which are also very important, and that those can be transformed into like some application that other engineers and so on will figure out in future. But I think that real world is really more about like thinking about what the problem that you want to solve and then looking for the solutions that already exist. So that would be that for me. What about you, Sai?
Yeah, to me, like a real world problem or a real world solution is the scale. Like, whatever we do, we build a product or a platform. So the impact it creates to the people, to the society at scale. So that is, to me, real world. So that kind of inclusive of all the infrastructures or the teams or members working in it. So that all clubs together if it can build a scale. So that's a real world solution to me. Yeah. Over to you, Sri.
Yeah, so I would start with a very popular meme here, which states that in the real world, the data is never clean and ideal. So I think that's the major challenge we face when we actually work on a real world project, that the data is not clean and it's not in the perfect form that we expect it to be when we are trying to fit machine learning models. So I think even before going into artificial intelligence or machine learning algorithms, it's very important to sort of process that data and bring it to a format that we would want to use to train our models, because at the end of the day, our models are only as good as the data that we train them on. So yeah, that is to me a challenging aspect of real world data science projects. And excited to share my experience of working on one particular such project with you all.
Okay, thank you, everyone. On that note, Rosana, will you please introduce us to your project?
Thank you so much. And again, thank you for DataQuest for this opportunity to be here. This is quite an exciting crowd that we have here today, and also very nice opinions about what a real world project is. So let's get started to see what a real world project looks like. This is our first case study that I'll be presenting. This was a project that was done with Omdena in collaboration through Dryad Networks, that is a startup in Berlin, in Germany. And the goal of this company is to detect forest fires, and for that they use sensor data. And then this project was done, of course, in a collaboration with a group of Omdena volunteers. And the goal was, as I said, like to look into forest fires, but with the caveat that we are trying to identify early forest fires. So as early as possible, as a matter of fact, and to integrate this, like we have those sensors, that is the IoT part of the Internet of Things, that are also integrated with AI. So we use the sensors to detect the fires with some AI models. And with this, our goal is to prevent forest fires to escalate, and of course, monitor the health of the forests. And this is, of course, aligned with several sustainable development goals, such as clean water and clean air, as well as wildlife protection. And of course, like the health of the systems and the people living around those areas, how the food supplies is affected by those forest fires, and also, of course, all the financial impact that the communities close by have when there are forest fires. So when we can prevent those, we are having a lot of sustainable impact in several sustainable development goals that are highlighted here in this image. So the way that it worked, this project was, we received data from the startup for sensors. And the way it works, like here you can see that there is an image of a tree, and then you have the sensors there. Each sensor, like each of those machines or those equipment actually have several sensors inside. So they detect a sort of like several kinds of like a gas, the gas signals and humidity and temperature and many other variables. And we received all this data, and we had the goal to identify which variables were the most relevant and create a whole AI pipeline or model that would be integrated to this device here itself. And the interesting thing about this project is that like we were first dealing with experiments. So this was not like we were obviously not setting a forest on fire to get the data and so on. So like we were doing experiments in chambers, like a small chambers where we would have both smoke or just clean air. And also we had like experiments like more in like a bigger hall room. So we had like, you see in the later we have like hall and chamber as two different setups or environments where these sensors were measuring the air basically. And our goal was to identify, so it was a classification problem, and identify, is this a clean air? So like is the forest that nothing bad is happening, or at least there's no fire? Or is it a gas scan of smoke and fire? So that was the main goal. So the way that Omdena works, it puts together a bunch of people from all over the world that are very passionate about social impact. And here you can see our team. So we were in total 35 people who finished this project, like from very, very different backgrounds, quite interesting crowd. And here we had to put together all these pieces, as I mentioned before. So we had to create a machine learning model from this data. Then that means that we had to identify which variables were relevant for us. We had to put up like a model that is like the best model for detecting those forest fires or detecting the smoke. We had to also tune those models to make the best that we can from them, and then of course put it all together into a product that we give back to the Dryad team. So this was what we had to follow, this kind of, so to say, pipeline here that I'm showing, like the different pieces of this puzzle. So data preprocessing, analysis, modeling, and deployment. That it's kind of like here a bit more summarized. So here the idea is like we had to split this problem into several tasks, which is a very typical thing that we do at Omdena. And as a matter of fact, in any data science team, you have a team that is more specialized in the knowledge, like who try to understand the problem itself, in this case of forest fires, like what does it mean to use gas and sensor data, what kind of methods are the best for that, identify what kind of problems that we have to solve, what models are good for identifying or classifying sensor data and so on. So this is this whole knowledge team doing, finding, for example, we needed to have knowledge about some specific technique or something. So those are the folks who would try to find the knowledge for us and to convey this to us. Then we had the pre-processing step that was done kind of like hand in hand with the analysis part. So we had two teams that were like at the same time identifying some peculiarities about the data, such as anomalies, such as missing values, and so on. And at the same time, implementing solutions for that. So for example, the analysis team would identify there are this number of missing values in this variable, what should we do about it? And then they would communicate with the pre-processing team that would find a solution for that and implement the solution to, in the end, create those two teams who are in the end putting this together into a data set that was passed over by the modeling team that was figuring out which models were the best to classify the sensor data into clean air or in smoke, and then put it all together into something that is like a really ready to use by the Dryad team. So that was the idea, and it was the deployment team that did that. So let's have a look into how this looks like in practice. So for the data pipeline here, this would convey both the pre-processing and the analysis team. So let's have a look. We had to, of course, like do some kind of like quality checks on the data that we had. So for example, we had to look into, like we had to, first of all, like extract this data that we received from the Dryad team, then identify what needed to be cleaned, identify like a kind of like a transform and homogenize the data, so to say. So for example, we had to go through some processing of scaling the data, of handling missing values, handling outliers, and so on. So one important step of our project here was actually looking to anomalies that would help us to identify, for example, some variables had too many anomalies, and then they would add much more noise to the models and so on. So we were deciding not to use in them. And here in this image, this is an example. So as I said, we had several readings. Those are like a time series data. So you have like for one experiment, so to say, could be, for example, in this chamber that I mentioned before, you have a chamber, sometimes you have clean air, sometimes you have smoke, because this is what you're trying to measure. So this was like created, so we can train the models. And then you had these sensors, like each kind of like a value here, or each variable here, is a different measure from a different sensor. And then here you have what is clean air and what is in smoke. So in blue here, you have what is like so to say, like what we would identify as a fire, and what is in orange was like a normal air in the forest, for example. And from here, we could identify that most of, like we had the gas, we had the humidity, we had temperature, and each one of those are like different measurements. And then we could see that some of those sensors had a lot of outliers. So here's the number of outliers for each of those sensors. And then we could identify that, for example, the gas scans had a lot of outliers. Also, like we saw for different scenarios, that humidity and temperature as well. And this, of course, influenced in the decisions that we made for the building of this model. So we also had to deal with imbalanced data. This is, as I mentioned before, a classification problem. So we had data from the chambers, we had data for the hull. So those two sets that we mentioned before, like two scenarios. And the amount of data that we had for in smoke, we had much more in smoke data in the hull. So we also had to make a decision of what we were going to do about this as well. And we could also like look into, like as I mentioned before, we had a lot of data, a lot of different variables, and we needed to see how they correlate with each other. I don't expect you guys to see like all those values here, but just to walk you through this image, this is a heat map that we're looking to correlations among variables. And here, the lighter it is, the stronger is the correlation. And what we saw is that, for example, several variables, for example, several of those sensors measurements from temperature correlate to each other, meaning that if they have all more or less the same behavior, doesn't make sense to us to add all of them into a model, because if we do this, we will be increasing the noise of the model, if you want, or we would be confusing the model with just much more like redundant information. So this helped us to understand which variables we can remove, for example, from our data set, and in order to get like only the most important ones. And then with that, we can put it all together into a final data set, of course, like after a lot of like decisions of how we split the data, which variables we will be using and so on. We had like, I think more than 20 variables originally in original data set. So after all this work, we managed to put it all together and finally pass it over to the modeling team, where we could then try out several models. We tried 7 different models, and to classify whether the measurements that we got were or not smoke and clean air. And here you see the results of those models. Like, those are the best 2 models that we had. And we actually created 2 classifiers that are different. One that is like, is it in smoke or is it not? And is it clean air or is it not? And the one important thing here was that we needed to also consider the size of those models, like after we trained them, because we were, remember, putting this into a sensor that is a small machine or a small device. And the size of the models in terms of megabytes or gigabytes and so on, it matters. So this is also something that is interesting to take into account. In the real world, we will not always take necessarily the most accurate model, but you also have to consider this kind of things into account. And after all of this, we put all of these models and the information into a container, into a Docker container specifically. And this was our final product that was finally delivered to the Dried team, with the whole goal of like, now you have everything, like all the requirements, all the libraries, everything that you need is inside this container, and then you can just take this and deploy in your device. So that was our goal. And the takeaways from this project, of course, we had a lot of challenges. We had to understand a bit how to think of this whole pipeline, how to deal with imbalanced data, how to split the data, how to, identify the relevant features and so on. So this is a little bit of what I showed you before. We also had lots of important skills, key skills, really to manage to finish this project, both soft skills such as like a teamwork, because as you can see, there were like several teams and they had to really communicate with each other. We also needed to think outside of the box and try to understand how we can solve this problem. We had to have this communication among not only our teams of technical people, but also get feedback from the stakeholders from Dryad as well, and see like how they want to build the solution. For example, this thing about the size of the models. And of course, like we had lots of technical skills that I will not enter in the matter here, because those are basically the ones that I mentioned. But those, like for this kind of problem, those are the skills that were relevant. And of course, we used several tools, and for version control with GitHub and XHub as well, and Python for programming, and the cloud for storing the data, and Docker finally for deploying our final results. And with that, I'll close. If you guys want to get in contact with me, this is my information. And thank you very much for your time. I'll pass over now.
Yeah, thanks, Rosana. That was a very interesting case study. So now we move on to the second case study of the day, which is developing species identification for mosquitoes using AI. So this was a problem that we solved for our partners. We at Omdena solved for our partners at vectech.io, which is a biotechnology company, which is mainly focused on developing AI-based surveillance tools for end-to-end detection and monitoring of vector-borne diseases. So the main motivation behind solving this problem is that millions of people all over the world are affected by vector-borne diseases, and many of them die as well because of this. Hence, in order to treat these diseases, it is very crucial to identify species of insect that is causing the disease. In this particular project, we focused on mosquitoes. And as we know that there are thousands of species of mosquitoes, and some of them just differ from the other species by a very minute body part. So it is very crucial to identify the species of the mosquitoes in order to treat those vector-borne diseases. So this is the motivation, and our partners at vectech.io already have framework in place which identifies species of mosquitoes. However, that framework involves a manual task of identifying the body parts of the mosquitoes prior to species identification process. And this is where we came into the picture. They wanted us to develop an algorithm for identifying specific portions of images of mosquitoes and segment them based on the body parts. What I mean by that is, for example, if you see the figure on the left, that is a sample image of a mosquito trapped in a container, which is captured by them. And our job is to develop an algorithm that would segment that particular mosquito image into several classes, or rather put masks and segment that image based on the mosquito body parts. For example, in our particular case study, we have these body parts: abdomen, background, wing, leg, thorax, etc. Background is not generally considered as a class. Apart from that, we have 8 different body parts that we need to segment given the photo or the image of a particular mosquito. In terms of, as a head start to this project, as I mentioned, that the data comprises images of mosquitoes trapped in containers collected from various locations and in various orientations. Some of these mosquitoes might have missing body parts as well, and they comprise various kinds of species of mosquitoes. It's really hard to tell just by looking at the image what species of the mosquitoes we are looking at. And the result that is expected out of this project is an algorithm that would be able to successfully classify that image of mosquito into various segments based on the body parts of the mosquitoes. So let's get started with the solution that we have arrived with for solving this problem. So in artificial intelligence, there's a set of algorithms called semantic segmentation algorithms, which exactly does this job. If you can see the image of this room on the bottom left, what a semantic segmentation algorithm will do is that it will take each pixel of this image and try to do a classification. So what I mean by that is I already have a predefined set of classes. For example, the classes denote various objects in the image. In this case, the bed, the curtain, the carpet, the dresser, etc., etc. We need to classify each pixel, whether it belongs to a particular class or in this case, an object or not. So you see that the outcome or the result of the semantic segmentation algorithm is the image segmented according to the various classes or objects. One thing to note here is that we do not distinguish between more than one instance of a single class or an object. What I mean by that is, for example, if there were multiple beds in this image, those two beds would be identified by the same mask color. So there is another set of algorithms called instance segmentation algorithms, which distinguish between two instances of the same object. But semantic segmentation is something which is relevant to our problem statement. And here, for example, if the mosquito has two legs or two wings, we do not want to distinguish between those two wings. Hence, wing would be assigned a particular kind of mask color, and legs would be assigned a particular other kind of mask color. So this is the motivation behind using semantic segmentation algorithms to solve this particular problem. And as a part of our project pipeline, we had mainly 4 stages, starting with the annotation of the data. So now that we've been given the mosquito data by our partners, our job is to annotate this data, basically label those masked regions of the or the mosquito body parts using polygon annotation tools. So CVAT and Scale Rapid are 2 such open source online tools that we can use for annotation purposes. Although we have seen towards the end of the project that Scale Rapid is way more efficient and accurate in capturing those minute details on the mosquito's body, which is crucial to identifying the species of the mosquitoes. Next, we have the data augmentation step. So as we know that annotation is a very tedious process, it is time consuming and involves manual effort. So whatever data set size we had finally after annotation, in order to increase the data set size, we use various augmentation techniques like flip, rotation, zoom, etc. to make the data set size more in order to train our deep learning algorithms. And as we know that deep learning algorithms require huge amount of data for training and for giving a satisfactory performance. So after we have the data annotated and generate augmentations, we prepare the data set and then feed it to the semantic segmentation AI models in order to do the segmentation task. Now, we can have various open source models for this. There's constant research developing in this area. The idea is to use all the state-of-the-art architectures on this particular data set and see which are the top performing ones, fine-tune them based on our data set, and then build an ensemble out of those two. So that is exactly what we did. In our particular project, there were 2 such models, UNet and MaskRCNN, which gave the best results on this particular mosquito data sets. And those were the 2 models which we went ahead with and generated evaluation metrics and compared those 2 models for finally giving our deliverables to our partners. Finally, in the deliverable stage, we delivered the annotated images that we annotated using those Scale Rapid and CVAT tools, the model files, the scripts, all hosted in GitHub, and also a demo as to how to run the models and customize the models, whenever new data is collected, how to fine-tune, generate inferences using transfer learning. All of that knowledge was also shared to our partners in the form of deliverables. So moving on to actually the data pipeline stage. As a part of the data pipeline, now we are only focusing on the data processing stage, even before the modeling stage. So data collection is something which we did not have in our scope as Omdena. So we already received the data collected, and our job is to annotate the data, generate augmentations, and finally deliver the data set in the required format. One thing I would like to mention here is that depending on the type of deep learning model that we are using for a particular case study, the data set would need to be in that specific format. What I mean by that, we have two models finalized for a particular case study, the UNet and the mask RCNN. So the UNet does not have any such constraint. We can directly feed the image data set, stream it using Python libraries, and the UNet would accept it. However, the standard mask RCNN implementation requires the data set and the annotated data set rather to be in the Cocoa.json format. That is where you can use the open source code of mask RCNN directly to generate inferences on your custom data set. One thing that is to be kept in mind is that you need to have the data set in the format that the model you're going to train on the data set with accepts. So this is pretty much about the data pipeline. Moving on to some preliminary analysis on this image data before we finally fit the models. So the dataset comprised images of mosquitoes belonging to more than 13,000 species with 1 or 2 images per specimen. Some of these specimens had missing body parts, and the data comprised mosquitoes in various orientations and sometimes images of empty cells as well. We had retained those images as well in our dataset because our model should be able to identify when there is no mosquito present in the image as well. And one more thing to mention is that there are very minute classes like palps, antenna, very fine hairs, which are crucial to identifying the species of the mosquitoes. So special attention needs to be taken care when predicting these classes by our models. So after the data set is delivered, we have two models, UNet and mask RCNN, which we have used for segmenting our mosquito dataset images. Moving forward to the modeling stage. So these two models, UNet and mask RCNN that we had developed, they are the state of the art in terms of semantic segmentation. And the evaluation metric that we had used for evaluating these models is the intersection over union IOU score, which basically tells us that the masks that we have predicted, how much they overlap with the original ground truth mask. So the more the overlap, the higher is the IOU score, and that is indicative of a better model performance. And in our final production stage, we have used a train validation test split of 80%, 15%, and 5%. And for UNet, we have used ResNet 152 as a backbone, and for mask RCNN, we have used ResNet 101 as a backbone. But again, these are customizable for us. These two architectures work the best for a particular custom mosquito dataset, which can again be fine-tuned when new data is collected. And we saw that data augmentation proved to be very helpful because the IOU scores actually showed improvement on the augmented data set. And finally, we use an ensemble of UNet and mask RCNN to predict the classes. Moving on to the results of the models. So we not only generated mean IOU scores, we also generated class-wise IOU scores. So we see that the model is more or less able to detect all the classes quite accurately. Although some classes like antenna, pulse, and legs have been, predicted with lower IOU score because they are very minute and need more data, to be trained and to be able to, extract those features. One more thing is the confusion matrix of IOU scores. So this is quite interesting because we normally see confusion matrix in the context of classification. How is confusion matrix of IOU scores relevant for segmentation? So this confusion matrix tells us that for each of the classes, right, here we have an 8x8 matrix because we have 8 body parts or 8 classes, and we have the prediction and the ground truth as the axis. So this confusion matrix indicates that for each class, the mask that we have predicted, what is the overlap of that mask with the other class masks? So ideally, if you are predicting wings, the mask for wings, most of that predicted mask of wings should overlap with the ground truth mask of wings rather than other body parts. So that is the idea of using the confusion matrix of IOU scores for a particular problem statement. So coming to the end of the second case study, some key takeaways from this case study. First, I'll talk about the challenges. As we know that deep learning models require a huge amount of data to be trained on, and the data collection and annotation can be time consuming and can require manual effort. And we also see that some of the classes are very minute in nature and require a lot of data for the models to be able to identify them. And they are very crucial to species identification of mosquitoes as well. Also, I would like to talk about the hardware requirements. So most of these deep learning models which run on huge amounts of data, they're already pre-trained, and we can use those pre-trained models, and using transfer learning, we can generate inferences on our data. However, they sometimes need to be fine-tuned based on our data set. And that's when we need good hardware resources like GPUs and TPUs. Google Colab is an excellent free platform, provides these resources. But if we have GPUs and TPUs in our local system, that is also a very good option to start with. Else, it might take a long time to run these models. And speaking of the skills required in this project, teamwork and cross-team communication is definitely a must-needed skill, because we have to constantly collaborate with the annotation team, the modeling team, to make sure that the pipeline is going smooth. Problem solving and data cleaning are also essential skills, because at the end of the day, we need clean data to train our models. For our particular project, data, or rather, since the data is in the form of images, we need some image processing techniques, which were used for generating those augmentations like flip, zoom, rotate, etc. Research on deep learning state-of-the-art architectures and fine-tuning them is the second skill required, along with Python programming. So by Python programming, I mean being able to manipulate data, or rather Python for data science, as well as object-oriented concepts in Python. These are two important aspects of Python programming that are needed if you want to develop an end-to-end computer vision project. Finally, deployment, and last and not the least, analysis of the results. This is very important. So once we have the results, we need to analyze them and generate insights and give recommendations. For example, in our case, what we observed was that some of the classes were being predicted well by UNet, and some of the classes were being predicted well by MaskRCNN. So what we can do is create an ensemble of these two methods. And for the classes where UNet is performing better, we can just use UNet for predicting those, because these two architectures are very different, and chances are that they detect features in an entirely different way. So using an ensemble was a great idea, and that's what we had recommended to our partners as well, and they were very satisfied with that recommendation. Finally, the tools required for this particular project. For data annotation, we had CVAT and ScaleRapid as the polygon annotation tools. And for image processing, again, Python and OpenCV are the most popular ones. As an IDE, I would say everybody prefers Jupyter Lab, Jupyter Notebook, Colab for running any machine learning or deep learning models. And particularly for deep learning models, the frameworks TensorFlow, Keras, and PyTorch are the popular ones, although it depends on your particular use case and which open source architecture you are choosing and your personal preference as well. But these are the most popular libraries out there in Python.
Thank you, Srirupa. That's great. We will, friends, if you have questions for Srirupa, that was a lot of information. It was beautiful. It was brilliant. Okay, great. Thank you so much, everyone. Our third case study, all yours.
Thank you, Darren, and fantastic, fabulous presentation, Sri. Of course, the biotech is a pretty interesting field and got a great scope for AI to operate and solve on. So thank you. Cool. So, okay, so before we get on with this presentation, the third one for the day. So what I understand is the audience here are quite versatile, either people trying to get into the field of AI and data science, or probably people are pretty good at modeling algorithms and techniques, but wanted to get a holistic perspective of the how AI solutions are built in real world and how it can be applied in the industry, right? So with that understanding, we'll approach this presentation. So one thing that I keep suggesting to folks getting new into the field of AI or data science is try to concentrate more on the what and why, right? What you're trying to build and why you're trying to build. That would define the depth of how you wanted to build the solution, right, at scale. Of course, this is pretty much goes with any of the field for that matter, but as a data scientist or an AI engineer, this is very crucial, because there is not going to be one silver bullet to approach a problem or give a solution. We might have to keep experimenting a lot and then keep that iteration going, so that what and why will keep you motivated, right? So with that, so let's get on to today's presentation. So you can't fix what you can't measure. I repeat, you can't fix what you can't measure. So one of an MVP, minimum viable product that we recently built for a social impact company on the sustainability space called Sustain Labs, is a engineering pipeline using NLP and machine learning to build a sustainability benchmarking system for organizations to become more sustainable. Now, what is the sustainability data? So sustainability data is a data about a company's non-financial performance and behaviors, which is environmental, social, and governance, ESG performance, and also about the impact of the organization's products, services, or the business itself to the environment. Now, why should companies become more sustainable? We'll approach this in a two angle. One is from a business aspect, business impact aspect, and from a social impact aspect. Now, from a business impact standpoint, an analysis from a CDP, Carbon Disclosure Project, states that S&P 500 companies with sustainability incorporated into their strategy perform better than those that don't. They see a 18% higher return on investment. Now, to take a classic example, I've taken 10K filing report of a Tesla for 2021. So in 2021, the Tesla's major revenue was from the carbon credits, which is close to 500 million. Because Tesla is an electric vehicle, the company does not produce any carbon emission. So Tesla generates its revenue by selling ZEV, which is called zero emission vehicle, and greenhouse gas emission, GHG, to other manufacturers to gain these benefits. So that's a very high level overview on the business impact standpoint. Now, on a social impact, in July 2022, right, which is last month, the global surface temperature was recorded the sixth highest in last 143 years, which is reached up to 0.87 degrees Celsius. There was a climate conference meet, COP26, happened during 2021 in Glasgow. Nearly 200 countries came to that conference and agreed on a climate pact to keep the global temperature within the reach of 1.5 degrees Celsius, evaluating four major factors. Now, as I talk about those factors, I would also appreciate you watching this transition. What is the difference between the global climate, the temperature can make between 1.5 degrees Celsius to 2 degrees Celsius, right? So the four main pointers that were discussed were to reach global net zero by 2050 and keep the 1.5 degrees Celsius within the reach, adapt to protect communities and natural habitats, mobilize 100 billion in climate finance, and to deliver Paris rulebook comprising of a climate impact. A Paris rulebook is basically an agreement comprising of the climate impact, which has these three major factors, which is to provide an enhanced transparency frameworks for the report for the business for reporting the emissions, common timeframes for the emissions to reduce carbon emission targets, and mechanisms and standards for the international carbon markets. Now, a team of 25 plus collaborators as part of Omdena, involving machine learning engineers, data scientists, domain experts, joined hands to build an MVP solution to create a sustainability impact for a better planet and accelerating time to market scope for our partners. Okay, so now in a nutshell, what we did as part of this solution is we collect these ESG reports produced by the company, submitted by the companies, and simply pass it to a NLP engine and extract the KPIs, which is the carbon emissions, energy consumptions, etc., and match them to the relevant indicators produced by the machine learning models. And then perform quantifier-based analysis, time-based analysis, and then standardize a sustainability metric. So that will act as a rating factor for the companies to rate where they stand today and how they can improve towards their sustainability goals and reach this net zero goal as a common goal. So that's the nutshell, right? So now coming on to the solution aspect. So this is a 360-degree overview of the end-to-end solution what we built. So we started with the data collection, where we did a web scraping of various data sources, ranging from the GRI databases, CSR hub, corporate social responsibility hubs, SASB, sustainability advisory for sustainability boards. I think I'm missing the terminology there, but yeah. So those are they kind of maintain the standards and then hold a database of the companies into the sustainability. So we basically take those information from these various databases and then go to the company's website, scrape the data, get those reports extracted from there, right? So we used tools like Selenium for automation, and the entire web scraped documents will all get into DAXhub. Now, DAXhub is again an interesting tool. So DAXhub is basically Git for data science. But it also adds the power to track data with the DVC, data version control, and also perform experiment tracking for the machine learning models, how they perform. So that's our DAG set. So we get all the data to the DAG set and then perform a data cleaning on top of it. Now, data cleaning, we did have multiple approaches because I would say, like, data cleaning is a kind of an underrated component in the overall ecosystem of this end-to-end machine learning problem, right? The better, the 60 to 70% of the effort gets into the data cleaning and pre-processing. So the moment you have your, like Sri was mentioning, cleaning of data. So the best way you can clean up the data will have your end solution as the best solution, right? So we had various techniques to go over. Some of them are listed. Some of the problems is what we have listed over here. It could be like chemical formulas when we're extracting the data from the documents. It could be like formulas like CO2s and stuff, which might not be recognized by the extraction engines, or we might get some wrong informations. We would also have some tabular extraction, images being misplaced. So there is a whole bunch of challenges that we used to face with the data cleaning. So we kind of overcome those challenges with a couple of techniques, like converting it to word dictionaries, keyword-based filtrations, and then we, on top of it, we perform parallelly data processing and data extraction, where we used a couple of computer vision and NLP methods for data extraction. Some of them were using OpenCV and ECOCR, where we convert them to image and then create an NumPy array, and then we create a bounding boxes for each of these components. And we do an OCR, and on top of it, get those entities out, right? So that's a general method. So we also have challenges in terms of the structure of the data, because if you imagine a document, PDF document, it's not going to be on the same structure. We might have a multi-column documents, tabular structures, and a lot. Right. So for multi-columns, we kind of use PyTesseract. We, of course, tried various other tools and methodologies using PyView PDF Miner, AWS Textract. But finally, PyTesseract seemed to be the best fit over there. And then for tabular data structure extraction, we used Tabular and CamDot. So those were really fitting the bill over there. And we also evaluated and used AWS Textract for extracting the tabular information. And then the final data set for the models is we extract those data and then build it as sentences, right? So those sentences are going to be the data set or the input for the model to extract those KPIs and the value indicators out of it. So that's the final end data set that we build. Okay, so once we have this data set, right? So we pass the KPIs and these collected sentences to the machine learning model. We use the transformer models like BERT and ESG-BERT to get the sentence embeddings. So basically, from the transformer models, you get the embeddings of the sentences and the KPI list. So these encodings are essentially the representation of the sentence in the vector space. And then using cosine similarity, we find the closest match of the sentence to a KPI and derive the results. And then we pass that results to the next components of the machine learning model, where we used a fuzzy name matching, which is a technique to identify two elements or entries that are approximately similar, but not exactly the same. So once we get that output, then we pass on to some of the named entity recognition models to extract the value out of it, like the key KPI indicators, like the energy, how much of the carbon emissions have raised or come down. So those kind of indicator inference we get, measurement and time, etc. And then we get that data out and build an analytical reports out of it for the companies to compare and understand where they belong and where they can get towards, right? So that's a kind of a end-to-end overall solution that we built out. So in interest of time, so I'm going to keep moving. So we talked about all these processing. So these are some in-depth processing. How do we did the bounding box capturing, and then did the OCR on top of it? How various methods to manage the multi-column PDFs, because for example, if you take the OCR engines, it might not be able to give you the sentences like how you expect over here. It has to bend and then it has to go here. But what might happen is you might get a sentence like in a horizontal end to end, which is no interest. I mean, it's going to confuse the model and it's going to become more crazier, right? So those are the problems and challenges that we have to overcome. Tabular structures, and then we did a data analysis, and the final data set is something which would look like this, which will derive the KPIs and predict the scores out of it. And of course, as we discussed, we would start with the KPI matching. Then we used dependency parsing methodologies to get those corresponding KPIs. Then we used a labeled data set for the BERT machine learning models to get the results of the KPIs to perform better. So yeah, so from a challenging standpoint, we kind of covered a bit. From a team top skill standpoint, collaboration is one of the very key factor over here, because people who solve these problems are from a various background, and then expertise, sharing of knowledge, and then brainstorming and getting to that one conclusive solution is not an easy task here. So that is something which is very important perspective. And irrespective of any kind of a solution that we build, one major challenge that we would have is we definitely need a human intervention to validate the final output. So that's, it's not just for this particular NLP solution, but any NLP solution for that matter will have to have some kind of a human loop to validate the final results and get things out. And okay, so I'll let you take a look at the tools, and I'm going to just pause it over here. So there are various tools we used, starting with Selenium, Tabula, PyTest, machine learning models, BERT models, and Prefect for building the end-to-end pipelines. And as I mentioned, DAXUP is a pretty interesting tool as well. Some of the future scope, what we wanted to do is we want to get that into Databricks, which is again a data processing layer, and you have ML flows for building machine learning models and hosting your models and registering, right? So that's a kind of an entire ecosystem what we have. So that's where we are heading towards, and it also kind of inlines with strategy of a particular company. In this case, Sustainlab, they were more strategical towards Google as their cloud strategy. So we'll have to keep ourselves aligned to the tools and methods that we use to support them and their strategic roadmap. So that's a high-level overview of how real-world projects are being implemented. I hope this gives you some level of a perspective and was helpful. And happy to take up any question, and you can reach out to me on LinkedIn and email as well. With that, over to you, Darren.
Okay, thank you so much, Sai. So let's take some questions real quick. We had a good one that I think applies to all three of you. And so if you would go back in order, Rosana, Srirupa, Sai, one of our friends here wanted to know what the time scale was for each of these projects. How long did each one take? So if you could just address that real quick.
So maybe I can go ahead. I think this answer goes to all of our projects. And that would be that Omdena hosts these projects for 2 months, so 8 weeks. And usually we have an extra time for documentation and everything towards the end. So like maybe more like 10 weeks in total. But ideas, of course, like here we are creating prototypes that not like that would be something that you would do like maybe in a company would take a bit longer, of course, because we kind of like give the first kick on the projects, and then the companies take over and move on with their own deployment in their systems and so on. But it would be about 10 weeks. Yeah.
So for case study 2, we had 3 months as the entire project duration. And for the data annotation and augmentation tasks, we kind of try to do them in parallel. So as soon as we have a considerable data set size, we would train our models and fine tune on that data set. And as people are annotating more and more data, we would sort of include that in the next training stage. So these are kind of parallel tasks, and the entire project took around 3 months to be completed. So that's 12 weeks.
Yeah, I mean, that's pretty much goes with other projects as well in Omdena. So even for sustainability benchmarking system, we did take 2 months, and all these projects really needs a very well planning as such. You can imagine. So all these has to go in parallel, and then we have to have a collaboration, and then also we have to iterate. So what we generally do is we take a first 4 weeks to quickly do all those exploratory stuffs in each of these tasks, and then we kind of combine on the midweek, 4th week, to get to see which of these best solution we can take, and then we can move the strategy or the roadmap forward, right? So that's a kind of a very well planning is required, and a collaboration and commitments from the collaborators to get this executed in such a short period. Yeah.
Okay, thank you. We have another question, this one from Mohammed. I think it really applies to all three of you again as well. I kind of like that sort of each of you in turn model. So let's try this. Mohammed wants to know, what stage was the most challenging in the project, and how did you figure out the solution? Rosana?
So I think that it's very common that the data processing stage is usually like, I mean, I know that like in terms of complexity of methods and so on, the machine learning modeling is always more complex. But actually putting all the data together, whenever you have real world problem, you have to really like consider that the data doesn't come clean and like already in a data set ready for you to use. So you really have to spend a lot of time also understanding, like even to come to the final data set that you use for your models, you have to really put a lot of thought on how you're going to clean the data, on how you're going to transform the data, and like which features are relevant and so on. So to me, at least, this is like for the forest fires, this was the most challenging part. For sure.
Yeah, so for me in our project, I think Implementing those semantic segmentation models was not that tough because the codes are available open source and research papers are also there to guide us. The challenge was after the first round of training, when we discussed the results with our partners, we sort of found out that CVAT as an annotation tool was not much efficient because it's not able to capture the minute details. So that's when we shifted to Scale Rapid, which is able to capture the annotations in a more detailed manner. So I think the challenge here was that is to bridge the technical aspect of it and try to understand the business problem, because the problem here is to identify the species of the mosquitoes, and it's very important to identify those very minute details. And just implementing a computer vision model and giving the results based on our understanding is not good enough, and we need to understand the business problem well and cater to the needs of particular business. So that was a challenge that we overcame for the second case study.
Yeah, I think for sustainability benchmarking, I'll also try to address one of the questions from Darshan Pai. That's actually the problem was we had a major challenge. So the field itself is kind of a very vast field, right? So with respect to ESG, sustainability, so you need really quite a heavy lot of domain expertise in understanding what are the key factors within those documents that are going to convert into a potential KPIs and benchmark from there. So that's pretty vast. It's not easy to kind of confine. So one is, of course, to have your data sets. You're going to have really heavy domain expertise in building your data sets. That's one aspect. But coming on to the question from Darshan Pai about the KPIs. So we started with defining a set of KPIs. For MVP, we started with the energy segment. Okay, with the energy expertise into the group, we kind of started with that, confining to that, and then if you're able to get to the accuracy. So that's how we started. But also we are kind of working on parallelly to get these KPIs in a more generic way, separate model pipeline for extracting these KPIs and keeping it generically, and then kind of tie these two together. So that's kind of an approach also we're kind of heading towards. So that's one of the challenge. Now, there are many other challenges, like in terms of extraction, as I mentioned. There's a lot of tools and methods that we kind of extract, but not one tool fits the whole ecosystem. So we have to kind of go a zigzag to choose a method for a particular use case, get back to another method, and then go back. So that's a kind of quite a challenging in terms of solution. And then on top of it, if you see the performance, just to do an extraction task, we need to kind of build a whole load of workload and ecosystem to scale the infrastructure to get this through more faster and rapid way, right? So those are some of the challenges, I would say, from the core extraction standpoint, as well as from an infrastructure scalability standpoint. Yeah.
Okay, thank you. Let's see if we can get one more round of questions in for each of you. Returning to Rosana, we have another question here. In the wildfire project, which metrics were used to evaluate the model? Do you have an answer for that?
Mm-hmm. So we actually were using the F1 score, which is basically to classify whether how many, because it was a classification problem, whether how many false positives and false negatives we have. So that's quite a standard methodology that we use in classification problems.
Okay, thank you. It's a general question. Do you have recommendations for data modeling tools? Excel, Python, Power BI, do you have a preference? Well, I think it's just a general question of which tools you prefer to work with, with Python, Power BI, Excel.
Yeah, what we generally do is, as part of these solutions, we take Excel is something which we use to define our data sets and extract and convert it to CSV. So that's a kind of a common format that we use to transform. Sometimes we kind of use JSON structures to build these models and then go about. It depends upon very much case by case basis how you wanted to solve the problem. Like in some cases we use graph databases to kind of build the solutions. So it pretty much depends upon the particular use case, how you wanted to solve the problem, and then that data modeling methods and tools is more subjective. Yeah, there's no one common way to solve a data modeling problem here. Yeah.
Okay. So we'd like to thank you all for coming, and thanks so much to our panelists for being a part of this today. And in the meantime, please feel free to reach out on LinkedIn. We're available. We can answer more questions. And I hope you have a great morning, afternoon, or night, wherever you are. And thanks again for coming. Thank you, everyone.